Hello everyone, I'm another coder and this is the fourth lecture in the basic algorithm series. In this lecture, we are going to study about searching, and more specifically, we are going to have a deep look at binary search. So, the prerequisites for this particular lecture are basic operation in arrays and sorting of arrays. So if you don't know how to sort arrays already, I would recommend you to learn sorting of arrays first. And I've already uploaded 3 videos on different sorting techniques. The first one is selection sort, then bubble sort, and then merge sort. Out of which, if you want to solve your program in less complexity, I would recommend using merge sort. Anyways, you will get the link to the playlist in the top right corner, the playlist of the basic algorithm series, and the first 3 videos are on sorting. So let us have a look at searching and what is the naive approach or the very basic approach, or what we call in this case the linear search. So for example, this is an array and we want to search for a particular element. For example, 1. I want to search for 1 in this whole array. First of all, let me mark the indexes. So these are the indexes and these are the elements. The indexes are from 0 to 6. So the size of the array is 7, and these are the elements or the data in the array. So for example, if I want to search for 1, the only way I have is to start from the first or the 0th index and check whether this element is equal to 1. If it is not equal to 1, then I move forward one step. Now I check if this element is equal to 1. It is not equal to 1, again one step forward, and again one step forward, and for the last time one step forward. And when I get to this index, this is equal to 1, so I return this index 4. So this is how searching or linear search takes place. This is a naive approach or the basic approach, what we call. Now, what is the problem with this approach? For example, the worst case complexity for this particular approach would be big O of n. Why? Because in the worst case, we will have to traverse through the whole array. For example, if we were searching for 2, then we will have to move from 0 to 2. And if the data is very large, then it is not a very viable option to use. So this algorithm has big O, complexity of big O of n, and in case n is very large, this approach would be very slow. So this is where binary search comes into picture. So as the term binary suggests, binary means 2. So we will be dividing this array into 2 equal halves, and again dividing into 2 equal halves, again dividing 2 equal halves, until we get one single element. Now the question is, how do we divide? As you can see that this array is already sorted. You will understand in a minute why we need a sorted array. You will see it for yourself when you see the binary search approach. So I've already taken a sorted array, and I'll mark its index from 0 to 6. So these are the elements and these are the index marked above. So the first step is to calculate the mid. How do we calculate the mid? We take the low index plus the high index divided by 2. In this case, 0 plus 6 divided by 2, which is equal to 3. Now, for example, if I am searching for 1, in the first step, I have got mid equals to 3. Now I check whether the element at 3 is equal to 1. In this case, it is not equal to 1. The next thing which I need to check, whether this element at 3 is greater than 1 or is less than 1, or in any general case, if it is greater than the value I am searching for, or it is less than the value I am searching for. If the value is less than 4, then I'll go to this half. If the value I'm searching for is greater than 4, then I'll go to this half, and obviously I'll discard the other half and divide the array into 2 parts. For example, in this case I was searching for 1 which is less than 4. So I'll move into this part and discard this part completely. Okay, so in this part the low would remain the same, which is equal to 0, and the high would become mid minus 1. Mid, which was in the previous case, and minus 1 would be the high for the next case. Okay, so after doing it, the low is equal to 0 and the high would be equals to mid minus 1, which is now equals to 2. So again we need to calculate the mid in this case. In this case it would be 0 plus 2 divided by 2, which is at index 1. So I check at index 1, if at index 1 is the value which I am searching for, it is equal to 2. I was searching for 1, so again I'll do the same process. 1 is less than 2, so I'll take the index 0 as low and 1 minus 1, which is again equals to 0, as high. So now you see I'm left with only one element, and in this case low is equals to high, where low is equals to 0, high is equals to 0, and mid is also equal to 0. Okay, so in this case I'll check if the element at mid is equal to the value I'm searching for. I was searching for 1, so finally I've got my value which is equal to 1. So there's one more important observation we need to make here, that when there is only one element, the low is equal to high. So we need to divide the array only if the low is less than high, because when low is equals to high, it is already one element, we cannot divide it further. So we'll only divide the array if low is less than high. This is the case, like this will be the base case when low is equals to high. This will be the base case for a recursion, and we don't need to divide it any further. Now this is the time complexity analysis of this particular algorithm, and it is very easy to understand. It's not much difficult. Like in the first iteration, the length of the array is n1, or the initial number of elements, I'll mark it as n1. Now at the second iteration, the length of the array becomes n2, which is n1 by 2. Why? Because we are dividing the array into two equal halves. So like there's one more important thing, that the number of elements at the second iteration or the number of elements after the first iteration, they're both the same things. You don't need to confuse like between these two terms, at the second iteration or after the first iteration. These two will be the same things, which is equal to n2 or n1 by 2. Now at the third iteration or after the second iteration, we get length of the array is equals to n3, which is equals to n2 by 2, which in turn is equals to n1 by 2 divided by 2. So at the third iteration, the number of elements n3 is equals to n1 by 2 square. If you want to form a general case, then after kth iteration, the length of the array would be equal to n1 by 2 raised to the power k. So like if we assume that there were total k operations in our binary search, then after k operations, the length of the array should be equal to 1. So here we equate these two things, like n1 divided by 2 raised to the power k should be equal to 1. So n1 would be equal to 2 raised to the power k. Now k is equals to log n. So this is the time complexity of our algorithm, big O of log n. This is how we calculate the time complexity for binary search. Now we'll have a look at the code. How does the code work for binary search? It's very simple. It's just the application of what we have learned. So just a while ago my recording stopped suddenly out of nowhere, and I have to record this part again, the coding part. So here it is. I just wanted to say that I'm really working hard for these videos. Please do subscribe if you like this content. Okay, so I had this array. I already have an array of size 7, and the elements present here are already in a sorted manner. So I'll create a variable index in which we'll store the index of the element which we are searching for. Now we'll call a function. Let us name this binary, and we'll pass the array. We will pass the low, which will be 0 initial case, and high will be equal to n minus 1, and we'll pass an element which we are searching for. In this case, let us search for 3. Okay, so we'll have to create a function which will return the index. So I have taken int as the return type. The function name would be binary. It will receive the array first, and then we had the low, then we had the high, and finally we had x, the value which we are searching for. So the first step is to calculate the mid. Int mid is equals to low plus high divided by 2. So this is the first step. Now the second step is to check if the element at mid is equals to the element what we are searching for. If it is equal to the element, then we'll directly return mid, will not proceed any further. Now if again L is less than high. This was the base case of a recursion, because when L is equals to high, there will be only one element and we don't need to divide it any further. So we'll proceed only if L is less than high. Now we'll check if array of mid is less than x. X is the value which we are searching for. So we'll return, we'll call this function binary recursively, and I've taken array, and now I'll change the low is to mid plus 1, high would be as it is, and we'll take x, the element what we are searching for. So as you can see, the element x is present to the right of mid, that is why it is greater than array of mid. It is present to the right of mid, so we will change the low as mid plus 1 and the high would be remain the same. Else in the other condition we would return binary, will pass the array, low would remain the same and the high would become mid minus 1, and again we'll pass the element what we are searching for. So like if we don't find the element, even if in the last case that array of mid is not equal to x, if it is not equal to x, then we cannot move into this, so we'll have to return a value minus 1 in this. So I've returned minus 1 because it can indicate that the element what we are searching for is not present in our array. So I think this program is complete. We can run it. So yeah, I have not completed it yet. There's a semicolon there and we need to print the index also, uh, uh, the value which the binary function has returned. So 2, yes, we were searching for 3, so 3 is present at index 2, 0, 1. This 1 is at 0, 2 is at 1 and 3 is at 2. So let us search for another number. I am searching for 7, 7 is present at 6. So we'll run this program again. Yeah, so 6 is the answer. Now let us search for an element which is not present in this array. It should return minus 1 in this case, so it returns minus 1. So you see, this binary search algorithm is not very difficult, it's easy to understand. It's just about the little concepts that are applied. You need to understand the logic behind binary search, and that's it for today's video. I hope you liked the content. If you did, please drop a like on this video. If you love the content, please do subscribe, and that's it for today's video. Keep coding, stay safe, stay at home. Bye bye.